This is G485 Homework Booklet, question 18. First of all, describe the piezoelectric effect. You're required to say that when a PD is applied across a material or a crystal, a piezoelectric crystal, it causes the crystal to expand or contract or vibrate. Clearly, an alternating potential difference will lead to a vibration. Secondly, describe how ultrasound scanning is used to obtain diagnostic information about internal structures of a body. Include the differences between an A scan and a B scan. Note that the mark scheme allocates 4 marks as a maximum total. 2 of them are allocated to the difference between an A and a B scan, and the other 2 can be selected from any 2 of these 4 points. This does show the importance of reading the whole question and always following question prompts like in your description include. So first of all, 2 from the first 4 points. Pulses of ultrasound are sent into the body. The word pulses is important here. The pulse is reflected at a boundary between tissues. And this leads to a time delay between the pulse being emitted and then later detected, and this time delay is used to determine the depth or perhaps the thickness of a particular region. Finally, the fraction of signal that is reflected, or you could say the intensity of the reflected signal, is used to identify the tissue. You may remember here and find on your datasheet that there is an equation for the fraction of intensity of a reflected signal. And note that it does depend on the 2 body tissues involved at a boundary. Finally, you need to make the point that an A scan is in one direction only, or that an A scan finds distance or depth. Whereas in a B scan, the sensor is used in multiple different positions and angles, and by doing this it can build up a 2 or 3D image. Next, you are given some data showing the speed of ultrasound in muscle and bone, and also the density of muscle and bone and the acoustic impedance of muscle and bone. Show that the unit for acoustic impedance is kilograms meters to the -2, seconds to the -1. You can look up on the datasheet the equation for acoustic impedance. It is density times speed within the material. Here we have the units of density in the table, and here we have the units for speed, which are fairly obvious, and combining them it should simplify to kilograms meters to the -2, seconds to the -1. Next, you're told that an ultrasound pulse is incident at right angles to the boundary between bone and muscle, and you're asked to find the fraction of reflected intensity of the ultrasound. This equation is on the datasheet where we have Z2 minus Z1 divided by Z2 plus Z1. So it's the difference in the acoustic impedances squared divided by the sum of the acoustic impedances squared. So careful substitution, selecting the right values from the table. We were looking at bone and muscle, and selecting the acoustic impedances that we have here. Leads us to an answer of 0.37 to two significant figures. Notice there are no units because this is a fraction. Next, what is meant by acoustic impedance matching? Explain why a gel is used to produce an effective ultrasound image. So clearly two parts to this question. First of all, acoustic impedance matching means that the impedances of neighbouring media are similar or the same. Secondly, why is a gel used to produce an ultrasound image? When an ultrasound pulse is sent into the body, if it had to travel from air into the body, there would be very different acoustic impedances. So the gel bridges the gap between the transducer and the body, and it reduces reflection at the boundary by matching the impedances. Alternatively, you could say this allows maximum transmission of ultrasound into the body. Next, a straightforward calculation. The frequency of ultrasound is given in megahertz. We're asked for the wavelength in millimeters. So just watch out for your handling of units. You're using the wave equation. Rearrange, that gives the wavelength is the speed divided by the frequency. And you had to select the speed in muscle from the table, which was 1,590 meters per second. Divide by the frequency in hertz will give you an answer in meters, and then you can convert that to 1.33 millimeters. Next, suggest why it is desirable to have ultrasound of shorter wavelength for a scan. Key point, the smaller wavelength gives a greater resolution. In practical terms, that means that finer detail can be seen.